Hello. So this is the last topic for chapter 6. We're going to go one step further. So last time we solved integer combinations of two any integers and then talked about how to determine when you can solve the problem and when you can solve the problem, what are all of the solutions. In this video, I want to tackle a problem that's a slight twist to that problem, where you're only allowing positive combinations of two integers. So let's jump right to it. Okay, so the book is calling it the dartboard problem, but there's actually a lot of situations where you want to ask something to this, something like the situation. So what if we only allowed non-negative integers for solution? So if for any a, b, and k, we want to look at solutions of m and n so that the am plus bn is equal to k. All right, so what do we know from last time? We know that if a and b, the greatest common divisor of those two numbers is equal to 1, so they're relatively prime, then they are solutions for m and n in integers. And we haven't talked about what happens if we only restrict to positive integers or positive also including 0, just non-negative integers. All right. So let me just give you the solution right off the bat. So the solution for relatively prime integers a and b is the largest number is going to be a times b minus a minus b. So this is the expression of the solution. So if they're not relatively prime, then there's actually infinitely many k's that they cannot achieve. But what you could do is in a situation where they're not relatively prime, you can divide by the GCD and get a relatively prime version of the same problem. So if it can be solved, then this will be the largest integer that's not solvable, and anything above it has a solution. Okay. So let's make a definition. So we'll say k is achievable if you can write it in terms of non-negative integer combination of a and b. All right, so to show that this is the story, the solution, I need to do it in 2 steps. So the first step, I should prove that ab minus a minus b is actually not achievable, that no combinations of m and n will actually give this number. And what I also have to show in step 2 that if you have a number that's larger than this, then it is achievable. It is possible to find a solution. So let's see how to prove step number 1. So this number ab minus a minus b is not achievable. Okay, so we're going to do this by contradiction. So first assume it is achievable. So you can write down ab minus a minus b in this fashion. And actually, you can shuffle this equation around a little bit. If you bring minus a minus b onto the right-hand side of the equation and collect like terms, you can rewrite a times b is equal to n plus 1 times a and n plus 1 times b added together. All right, and we know that a and b are relatively prime, right? So here's what you can conclude from it, right? So this guy right here is divisible by a. This guy also is divisible by a. So this guy minus this guy, which is this guy, has to also be divisible by a. But A divides n plus 1 times b, but A doesn't divide b because they're relatively prime. So that means that because of the lemma we proved earlier in this chapter, A has to be able to divide the other factor, n plus 1. And you could do the exact same argument to show that the b divides n plus 1 as well. But this means that I mean, if A divides n plus 1, that means A has to be smaller than n plus 1, and B is less than n plus 1 as well. Or they don't have to be less, it could be equal to them. So it's less than or equal to those numbers. So we have A is less than or equal to n plus 1, and B is less than or equal to n plus 1. But that's actually enough to get a contradiction. So we have A times B is equal to this expression. And this part is greater than or equal to B. So we can, if we replace with B, I'll get something smaller. So I'll get A times B there. And here, if we replace n plus 1 by A, again, I'll get something that's smaller or not any bigger. So we get A times B plus A times B. But if you add them together, that's 2 times AB. What we showed was A times B, which is a positive number, is greater than or equal to 2 times AB. This is a contradiction. Right? So this expression right here must not have been achievable. Okay, so let's get to step 2. If you have a number bigger than this, strictly bigger, then it is achievable. Okay, so this is what we want to show. So K greater than AB minus A minus B implies K is achievable. What we're actually going to prove is the contrapositive version of this statement. So it's equivalent to say, if we show that K is not achievable, then that means that K is less than or equal to AB minus A minus B. So remember, contrapositive is on the implication statement. You flip the hypothesis on the conclusion and put the negation in each of the statement, and then it's equivalent to the original implication. So that's what we're going to prove instead. All right. So say that K is not achievable, right? But because the GCD between those two numbers is equal to 1, it is possible to find an integer combination equal to 1, but just keeping in mind that when we solve these things, it has one of the coefficients has to be negative. There's no both of them non-negative solution, but maybe you can find a solution with one of them being negative because we already know that we can by the lemma earlier in the chapter. And then if you multiply by K, you can solve the integer combination problem. But again, the coefficient has to be negative, right? At least one has to be negative. Actually, exactly one of them is negative, and the other one has to be positive because two negatives don't add up to a positive number, right? So one has to be positive and the other negative. If you think about this a little bit, that means that if you kind of graph your solution in the M and N axis, that means that the solution that you get is either, it should look something like this. There's infinitely many solutions to these guys. And if exactly one of M or N is negative, then you are actually in the second quadrant or the fourth quadrant of this Cartesian plane. Okay. And we already saw how to get infinitely many solutions from these. So every time you increase the m by b units, you subtract a from the n, and you can get another solution. And you can go vice versa as well. You could subtract b and add a, or you add b, subtract a, add b, subtract a, add b, subtract a, and you can get this infinite set of solutions, and so on. And we're saying that the solution never hits the first quadrant, because there's no solution where m and n is both non-negative at the same time. So the solution should look something like this. All right. So let's say this solution, let's focus on this guy. I'm going to call that guy m prime, n prime. So this is the last solution in the second quadrant before, if you add b and negative a, then you go into the fourth quadrant. So it's the solution in second quadrant that's one before jumping into the fourth quadrant. Okay, so let's look at that solution for a bit. Because m is negative, that means m prime is less than or equal to -1. We know that. And also, we know that one step afterwards, if you subtract a from n, we go to fourth quadrant. We also know that n prime minus a is less than or equal to -1. So those two things have to be true. But now let's write down what this means. So k is m prime a plus n prime b. And m prime is less than or equal to -1. So if you substitute m prime with -1, we'll get something that's bigger. And we could say the same thing about n prime. So we know that n prime minus a is less than or equal to -1. So if you bring the negative a to the right-hand side and say n prime is less than or equal to positive a minus 1, and then substitute that for n prime, we get something that's bigger as well, right? But this expression right here, if you multiply it out, this is exactly a times b minus a minus b. So k is less than or equal to this expression. So I hope that made sense, right? So this is the largest number that's not achievable by two relatively prime positive integers a and b. So I think that's interesting problem. This guy has a name. It's called Frobenius number. It's the largest number that's not a solution to this type of problem. And I have a challenge problem for you. So this is a slightly harder version of the problem, because now I'm giving you 3 different numbers. So in McDonald's, you can order chicken McNuggets in size of 6, 9, and 20. If you discount the Happy Meal size, which is 4. I think it's more interesting with just these 3 numbers, 6, 9, and 20. You can't really reduce this using GCD, because there's no GCD for all 3 of these numbers. That's going to be 1. So try to figure out what is the largest number of chicken McNuggets you cannot buy in some combination of 6, 9, and 20. So I'll leave that to you. The solution, the Frobenius number for this problem, it's called McNugget number. And it's surprisingly larger than you might first imagine. Anyways, try it out. It's a fun problem. I will see you guys next time.